Okay, that is better. The way that I like to do the term review is very informal. What I mean by that is that it's meant to be something that is beneficial for you to study for the term. So if you happen not to be following, it might be better for you to just go and have dinner instead of like sitting here. So won't offend me at all if when I'm talking, and then you can just walk up and then leave. That's fine. And I'm going to be uploading just like the lecture. I'll upload everything that I wrote, and then you can have that. And also, if I remember, okay, recording, and then I'm going to upload the recording as well. The way that I did it was that I had all your email and then compiled them chronologically now. So you should have this journal file that I sent out about 4 o'clock. So you can follow that with along. Another thing that I want to say is that I'm going to be doing it systematically, but then do stop me because it's informal. If you have any question while I'm talking about that and then I didn't address that, ask that question right away, okay? And then after I've gone through this one, if we have time, if someone still is in this room, so I'm glad to address them. The first one, I'm not going to say anything because Dr. Hammershey already said so. It's not going to be anything that you didn't hear, anything that is foreign from the lecture that is on last year's term, you probably won't want to be seeing it. Or you will not be seeing it. It is not. All right. Do you have to learn the actual names of the enzyme? The way I do it is that whatever the abbreviation I use, like I mentioned alpha kg a lot instead of alpha kilobutyrate. So I expect you to know alpha kg as alpha kilobutyrate. Some of the terms that I might think that you might not be knowing it as much, but then I think using it not that much, like PGI. So I will just spell it out, phosphoglucose isomerase, just to let you know. So if you follow the way that I deliver the lecture, that will be the way that you will see on the exam.
Also for the enzymes for the citric acid.
Yeah.
I mean, this I don't remember what it is. E1, E2, E3.
Yes.
Pyruvate.
Yes. Since
can we just know it by?
Yeah, good. That's a good, excellent example. For the pyruvate dehydrogenase multi-enzyme complex, I rarely mention the name of E2 and E3, and then I only mention like E1 is pyruvate dehydrogenase. So when I construct a question, I will explicitly say that if I use that, it's E1, E2, and E3. So very consistent with the delivery during the lecture that the terminology I use. Similar to terminology I use during lecture. And also, keep it that way. Will there be questions similar to our lab on the midterm? Normally, for those questions that are more thought-provoking, is something that is more like use what you learned during lecture in order to think through to address those questions. Those are the questions that you're not going to see it on the midterm. However, a lot of those questions, conceptual questions based upon the lecture, for example, a lot of them are the enzyme kinetics questions. Definitely you will see on the midterm. So it depends on which type. Sometimes it gives you extra information in the lab just to construct a picture. Those kind of information you do not need to know. Anything related to the concept, you must know. Remember, ask me a question if it's not clear. Okay? Very important. Very important. It's not lecture. Okay. what is the definition of a coenzyme? That is with respect to the cofactor. The way that I'm using it is that cofactor, it can be metal ion and coenzyme, or small organic molecule. So that would mean that coenzyme would be always right if it is something that is necessary for catalysis. Coenzyme is always correct. If the molecule is small organic molecule, then cofactor is always correct. So if it is a small organic molecules, then it is coenzyme to be a lot more specific. But then just that because the way that people are using the word cofactor is very generic. Any molecules that is required for catalysis outside of the polypeptide is the cofactor, and that's why it's generic from that perspective.
What is ATP an example of a cofactor then?
Okay. The question is that would ATP be an example of a cofactor? And normally ATP is considered to be a co-substrate, and also depends on how people name it. And a lot of times, if a molecule that is eventually formed as part of the product, it is not the substrate, it will be the co-substrate. But again, that is not always true. Because I have mentioned about CoA-SH, right? CoA-SH is used in pyruvate dehydrogenase multi-enzyme complex, and it is coenzyme. But then it's part of acetyl-CoA. So then actually, from that part, it's ambiguous. You can call it co-substrate, but then it's more so people addressing it as coenzyme. But then in terms of the term cofactor and coenzyme should be pretty straightforward. Anything that is more ambiguous, then it might not be a good exam question.
No, I actually figured it out.
Okay, good. All right. I'm touching the mic. Okay. So the next one is to go through the mechanism of catalysis of lysozyme. So basically, then I'll go through it very generically. So drawing the structure of just the two ring of the structure of the alternate sugar, D ring and E ring, binding in the active site of the lysozyme. First thing happened, we have the glutamate 35. Proton protonating the oxygen. It is important that this part is a half-fold conformation. Why? Because if it is a half-fold conformation, this carbon and this oxygen is on the same plane, then electron can come down and then allow to pick up the proton that is protonated. So protonation of the oxygen here is a general acid. By doing this now, we see the D ring is leaving with the O, H. I mean, not the D ring. E ring is leaving, and then leaving the active site with the D ring. Now electrons coming down, right? And then it's positively charged. Okay. And then the next thing, and this one can do resonance stabilization to have carbocation, and then electrons go back to the oxygen. Okay. And to further stabilize this unstable transition state, then the aspartate 52 would attack the carbon, and then the electron go back onto the oxygen. And I drew this structure is on the oxonium ion, this nucleophilic attack, because you can see the electron moving. And then it will be the same as this figure that mentioned on directly on carbocation. Yes, same thing. But then this might be chemically speaking, this might be more understandable.
Question.
Yes.
Yes. In terms of like the aspartate and so do we need to know specifically the aspartate or can we just is it okay if just remember a general base or general acid? Do we need to know
Okay, the question is that do you need to know specifically, in this case, the lysozymes catalysis, you need to know the glutamate 35, aspartate 52? Yes, in this case, because they do illustrate the mechanism well. So you need to know in this case, yes. So after this attack, this is the one that forms the transient covalent bond. So draw it to the next structure. Ring D. Now this is stabilized because it gets rid of the positive charge that was generated in the first place, even lower the energy content is TS. Now we see the same residue that was acting as the general acid glutamate 35. It lost the proton to the oxygen protonation in order to make it a better leaving group. Now it's a charge. It activates the water molecule to be more delta negative. Okay. Now this molecule can now attack and then break the transient covalent bond and then now form the product. So this glutamate 35 is acting as general base because it is pulling the proton from the water to activate the water molecule. Any question on the catalysis on lysozyme? Yes?
For the half bowl, is that the same as a half chair?
The question is that when I say half bowl, would that be the same as half chair? Yes, if you refer to the D ring structure. Because the other half is chair conformation, the other half is a bowl conformation. That's why it's half bowl, half chair.
Question.
Yes?
The half, so the purpose of enzyme doing making changing conformation to a half bowl is to raise the energy level, so it's easier to break it like that one for glycosidic bond. Is that what's happening?
Okay, the question is that if it is in the half bowl conformation, the energy level must be higher because naturally it likes to be in the chair conformation. So is that unfavorable? Would that be the question? Okay. So yes, normally this is solution is unfavorable. However, because it is binding in the active site of lysozyme, because of the low-flow interaction of the hydrogen bonding and the van der Waals contact, actually the half bowl is more favorable because of a favorable interaction. So it just active site environment caused the ring D to be in a more favorable conformation, which is a half bowl, even though in solution that is high energy.
But if the half bowl is going to be more favorable than the active side, then why is it that it helps with the the oxygen is glutamate comes in and stabilizes it, and the whole point is to break that one for glycosidic bond, right?
Yeah, good point.
So yes, right there.
Is
So
to break this bond, yes, this bond is let me finish writing this bond, yes. So break this bond, yes. Yes.
So it doesn't have to kind of raise the energy level of that enzyme doesn't have to do that in order for it to go forward, to become more unfavorable, so that's why it's kind of breaking.
If you look, the question is how do you look at the energy level for enzyme catalysis? then in general, in any enzyme catalysis, the enzyme active site is lowering the free energy content of the transition state. That's how it can form more readily. And in this case, it wants to break this bond. So the both conformation here allow the localization of the electron, weaken this bond. So that in close proximity of the side chain of glutamate, now proteinate, this bond will be broken. So then everything work in conjunction with one another, so that now this bond is broken more favorably.